All right, good afternoon. So let me give you like an overview of the course, and I'll also tell you some of the rules, and then you can ask questions. First, let me start with content. So this course is pretty much all about light. Like if you want, you can consider it like this course, including relativity, quantum mechanics, and matter waves, all of these things. We can base the arguments to light. This is about light, or more specifically, nature of light. And this is, I think, all of you probably have been curious about, right? It's everywhere, and for since ancient times, people ask questions about light, and even today we don't know exact answer, right? There are like so many things to talk about light, and maybe I can list some key cornerstones, maybe historical developments. So this is by no means accurate. My dates are probably not correct, but that's generally the case. History of physics is as complicated as physics itself. Who did what and when is generally controversial, but bear with me, the arguments are more important than historical accuracy. So we can start from ancient Greek, but I don't like that, so I'll start from the modern times, and modern times for me is like 1600s. And I think even before him, people thought about this, but I think the first person to think about is Sir Isaac Newton. Leaders of science, he also thought about light a lot, and his theory was light was composed of little billiard ball, little particles that just flow through space and come to our eyes, and we see an accumulation of a dust of particles coming to our eyes. It's like his theory was light was composed of particles. And this will be a central theme in this course. What is particle and what is wave? We are going to be spending a lot of time. So for the moment, let me not indulge on that too much. And 1600s, actually late 1600s, maybe almost 1700s. But in the 1700s, maybe early 1700s, you can check Wikipedia for more accurate information. But people like Huygens and Thomas Young, they suggested light is not particle like what Newton says. They suggested light is a wave. And especially Young had a pretty strong argument for this. He had so-called Young's double slit experiment. And we will also talk about this double slit experiment a lot. It is one of the core concepts in entire modern physics. And I think physics today chose it the most beautiful experiment of all times. They asked hundreds of leading physicists. And I think number one was double slit experiment of electrons, which supports quantum phenomena, but I think it's also double slit experiment. We can do it with light. So it is a very simple yet very powerful experiment that disproved Newton's conjecture that light is not particle. So if light is wave, there was the question, right? Waves, the kind of waves we know around us is I think most familiar is water waves, because if you went to ocean, we have seen the ocean waves. And the ocean waves is just periodic motion of water, right? Water, every single water molecule is stationary, but their collective motion gives rise to some kind of motion, something moving, and that's what we call wave. If that's the case, the question is, if the light is wave, what is waving? We are also going to be spending a lot of time for this question. But for the moment, let me not talk too much about that. Okay, many things happened. I will not be very accurate. Like I said, let me just go to next 100 years, like 1800s. And I think undoubtedly, at least for my taste, the most important thing in the 1800s is theory of electricity and magnetism. Electricity and this is where like physics as we know today starts to take shape, in the sense that electricity and magnetism, there are like many big names contributing it, but there is no one single name. There are like many contributors, like maybe I can list a couple: Coulomb, Gauss, I don't know, Faraday, etc., etc., etc. But the person who made the biggest paradigm shift was, again, Maxwell. And he showed basically two things. One, electricity and magnetism are unified. This is, I think, the biggest thing. What you call electricity and magnetism is the two faces of the same thing, right? They transform to each other in one way or another, but you can just have one concept that governs all of these. This is probably the subject of freshman physics 2, second semester, but I will not be talking about this too much, at least today. But what was more revolutionary was electricity and magnetism obey wave equation. This we are going to derive. Like you take the Maxwell equations, or like Gauss's law, Faraday's law, Lenz's law, all of these things, you can take this, and in the empty space means no charge, no current, you can manipulate these equations to obtain a wave equation. We are also going to, if you have never seen a wave equation, don't be scared. That will be, we are going to be talking about that a lot. But the most revolutionary result about this wave equation was the speed of wave. Right? Exactly like the waves on the ocean, right? They propagate in a certain speed, which is completely determined by the properties of the medium. There is also a wave speed coming from the Maxwell equations. And Maxwell calculated that, and we are going to see shortly how he did it. And in some miraculous way, he found that it was the speed of light. And at his time, speed of light was more or less known. Not to ultra precision we have today, but they knew it to I don't know, maybe 99% accuracy. And this was I think probably one of the most important developments in 1800, because now what we are saying is the light, for thousands of years, people wondering about it, right? What is it? Is it particle and is it wave? Maxwell said, oh, actually it is electricity and magnetism. It is exactly what Coulomb saw in his lab. It's exactly what Faraday saw. It's just electric and magnetic fields, they propagate in space. And when it comes to our eyes, we see the result. But of course, this was theory. And like any big physics concept, a theory by itself has zero asset value. Nobody cares. Even if you have the most beautiful theory in the world, I think nobody will ever care. And the important thing is experimental verification. An experiment for this Maxwell prediction came from Heinrich Hertz. Okay, I may have a hard time pronouncing his name, and he's the guy who invented antennas, right? Radio waves, antennas. I think we are in the digital age. Nobody is using radio waves now, but I think they are still used. And he invented those to prove Maxwell equations. So proved Maxwell using antennas and radio waves. Now you have like, okay, light is a wave, and it is a wave of electric and magnetic fields, right? And there's still the question, what is waving, right? And that was the most pressing question in 1900s. And 1900s was basically the subject of this course. When we call modern physics, we mean 1900. Actually, more specifically, the first 25 to 30 years of 1900. And you may believe it or not, many things happened after that, but nothing was as important as, even today, nothing was as important as what happened in the first 30 years. And in the one of the early pressing questions, that maybe I can draw you like, here's the water wave, right? You have like a bucket of water. And when you see these oscillations on the surface, you call it wave, and you know, right? As soon as you see that, what I see is just like kind of like an illusion, right? There's like water, every single water molecule is just where it is. I see something moving, but actually nothing is moving. So this is how we understand water waves. And in the 1900s, if light is oscillations of E and M, so what is the medium? Right? You need a medium for something to oscillate, exactly like this picture. And the very common suggestion at the time was so-called ether. Ether was like a substance that like permeates the entire space, exactly like water permeates the entire ocean. We can't see it, but it is like fixed, right? Exactly like water waves are fixed in the ocean, like water molecules are fixed. Ether is also fixed. And the suggestion was like we can't see it, but it must be the reason for this light waves. But like, of course, like I said a minute ago, like a suggestion, no matter how good it is, has to be verified experimentally. It is like non-negotiable. If you can't verify experimentally, it doesn't exist. And people looked for it, and I think the most convincing experiment was so-called Michelson and Morley, and they used more advanced techniques like so-called interferometry and optics, like so-called precision optics, like early versions of the precision optics we have today, and they found no evidence for ether. Okay, so you have some kind of wave, but there is no way you can find what is oscillating. And I think after Thomas Young and then Maxwell, and then the third biggest development came in 1905. 1905, I think this is like a common knowledge now, everybody knows. What happened in 1905? What's that? Yeah, Einstein happened, right? So Albert Einstein came. And he said, no ether, there's no ether, I don't need ether, he said. And he developed a special theory of relativity. And we are going to be talking about this theory for the next 2 weeks. It is also like, I think Albert Einstein, when he did it, I may be wrong, but I think it's 25 or something like that, 26. And you are explaining one of the biggest puzzles in the history. You are like almost like teenager, and he used like more or less high school algebra. He didn't use integrals, he didn't use, I don't know, eigenvalues and matrices. So maybe I will, I think some of you will have like a difficult time with this course, and you'll blame mathematics and like your background and stuff like that, but remember that you actually don't need much background. And maybe this is one of the core aims in this course, to show you that these interesting stuff you can get into without knowing too much. And I'm not going to expect you to know advanced mathematics. So this is the 2 weeks, but in the later, okay, so this kind of is going to be end of discussion, like light is a wave, right? Once we see this, we know every aspect of this light phenomena, and we are going to say, okay, light is a wave, period, end of the discussion. Light waves. But later, okay, later, like maybe week 3 to 14, we are going to see this is not that simple, right? We'll see like a dilemma. This will reoccur, right? We'll have to just come back to this. Is a particle is way over and over again of particle and wave. And the first, again, I think this one is like an experimental revolution, like so-called Max Planck explained so-called black body radiation with light particles. When people thought the discussion was over, and when people were most sure, like 100% sure, light is a wave, something else happened and people went back to the beginning. And now light is again a particle, right? And he invented so-called quanta, and it gave rise to quantum mechanics. And it is not just black body radiation. Many experiments. We are going to talk about like photoelectric effect. We are going to talk about Compton scattering and many other experiments. There will be a huge catalog of experiments I'll expect you to know by heart, and they all point towards the fact that light is actually a particle. And then people at this point started to consider maybe light is both particle and wave. Later it is like, I think, so this is before 1910, you can check the Wikipedia again. Later Niels Bohr came up. I think this is 1910s. I think I didn't write the exact date. Niels Bohr also now, okay, light, which was confused, right? Is it wave, is it particle? Niels Bohr like, okay, forget about light. Let's consider matter. Matter, like I said, this water, this table, your body, me, this, I don't know, the walls of this classroom, and also like electrons and atom, and also like so-called spectra. You probably know what spectra is from high school, but don't be scared. We are going to talk about that. He said all of these things can be explained wave nature of matter. Okay? A minute ago we were thinking about something is wave, or maybe not, what is it? And now the most familiar thing, which is like a particle for all of us, electron, atom, all of these things like existing matter, maybe he's like suggesting it is also wave. And this idea was taken to a step forward by Louis de Broglie, and he proposed what Bohr said in like clear terms, matter wave. All matter is both wave and particle. And of course, what Bohr and de Broglie did was like very compelling. They were explaining many experiments that were unexplained prior to them, but they still didn't have like a theory that's like systematic and applicable to everything. And this came later. I think it's like almost 1920s, and this was done by Schrödinger, Heisenberg, Dirac, I don't know, Jordan, Born, and many other names we are going to talk about. And they developed modern quantum mechanics. And we are going to be spending a lot of time to understand that. Of course, with minimal mathematical requirements. And this theory is so powerful, like I think, say it was developed in like 1925. After like 100 years, it is almost unchanged, right? Not only we are using exactly the same theory for like this class, for example, but also we are using it for research, right? Some of you are going to continue in physics and you are going to do research and you are going to of course, there are many things in physics to do research about, but if you're interested in atoms and materials and matter and all these phenomena, you will apply quantum mechanics as it was developed by Schrödinger, Heisenberg, and Dirac. And the reason for this is it works, right? It works. Like for 100 years, people tested it in like hundreds or thousands of maybe experiments, and it works every time. And it works, for example, to explain electrons. We'll see in detail how it works for hydrogen. And we are going to make it more complicated, and we are going to show it works for like it works to explain many electron atoms. And like at the time, like Mendeleev developed periodic table, and chemists know about elements already, but they didn't know why it was like that. And it also explains periodic table. It also explains molecules, probably more complicated molecules like organic compounds. It probably explains biology. It probably explains you. Your entire existence can be explained with quantum mechanics. At the moment, we can't do that, but we have pretty good reason to believe that that's the case. Like molecules, solids, all material. Also liquids, gas, for example, magnets. In some sense, people are going to push you like some big ideas in physics, like theory of everything, learn this, learn that, mathematics. Maybe I would like be happy if you can remember, we actually have a theory of everything already. It's the quantum theory, but in general, we cannot solve it. And we have to do a lot of like training to be able to solve it in like different circumstances. So this is the content.